So our project was medical imaging, which is a CNN project. And basically what this does is you input it an X-ray photo of the chest, which is in black and white, and then it's supposed to output a binary classification. Does someone have pneumonia or do they not have pneumonia? Um, and the baseline model for this was really solid, with the train accuracy and validation accuracy being at 95% each. And the loss was reasonable, not being that high. Um, we changed a few things in our early custom model, and we saw that the train accuracy went skyrocketing. Our validation accuracy didn't move too much, and our test accuracy went up as well. But in the loss, we saw one big issue, and that was in our validation loss, where instead of decreasing like the train and test loss did, it went up by 1.5x, meaning that our data was significantly overfitting. And so we changed a few more things and we got to our final custom data. And that model, we saw an increase in all of our accuracies as well. But we didn't have the issue of the validation loss being super high. It actually went down by about 0.13. And you can see this in our bar graphs here. On the figure 2, the baseline is less than our early custom model and our final custom model. And in figure 3, the baseline is always greater than our final custom model, which is what you want to see when you're trying to have the most accurate data.
Okay, now looking at the loss in accuracy curves for our initial baseline model, we can see that it's overall underfitting, which means that the model needs more training. So from our baseline model to our early custom model, we raised the number of epochs from 12 to 16 in hoping that the model would be trained better and more efficiently, along with increasing the number of convolution blocks and the dense layers. However, this led to overfitting, as you can see in the loss in accuracy curves. And overfitting is essentially when the model is memorizing the training data rather than learning the features and being able to recognize and identify it on unseen data. So to reduce this overfitting in our final custom model, sorry, we reduced the number of dense layers from 2 to 1, but we also increased the number of neurons in the single dense layer from 64 to 128 to maintain that same complexity. And we also reduced the epochs again from 16 to 12 because we found that increasing the epochs often led to overfitting in our graphs. And with our final baseline, we see a relatively smooth curve and only slight overfitting at the end. However, as Kai was talking about earlier with the accuracies, we can see an increase in accuracies over all categories, train, validation, and test, and a good drop for all the losses among those categories as well. So we settled for this as our final custom model. Some of our takeaways. I think when we were doing all of our runs, people tend to focus on the training data more. Sorry, I'll go back to it right now. But we found that we really have to focus and look at our validation metrics because even though the training accuracy shot up really high for our early custom model and the training loss dropped like tremendously, the validation loss shot up, which meant the model wasn't generalizing the data. So it wouldn't perform as well on new unseen data. So we had to really focus on those metrics.
And our other takeaway is how important depth is to a CNN model. Most CNN models have really good feature recognition. They can tell if you have a dog or a cat or a stick, right? But they really struggle with looking at color and being able to differentiate between pneumonia or normal, or if someone has lung cancer. And so having a good CNN that can detect pneumonia has to also be really good at detecting depth and being able to see different levels of grayscale in a way.